Hello everyone, here's the start of a chapter called Chemical Kinetics. In other words, the speed at which chemical reactions occur, okay? Somewhat of a standalone chapter here. So let's take a look at this. And the first thing we're going to look at is something called reaction rates, okay? So rate, this is the first and only time that you'll talk about time in AP chemistry, okay? So rate is typically something that's like a physics thing, but if we're going to talk about how fast something goes, we have to talk about time. This could be in minutes, seconds, hours, even days, okay? So let's take a look here. So when we start off with this, we take a look at reaction time as happening over, again, a period of time. So if you take a look at this reaction, let's see, it says the reaction is, it looks like it's A converting to B, okay? So A is converting to B, so we have 1 mole of A, and obviously a ton of that, and as time goes on, we have to monitor this change. The question is, are we going to monitor the deletion, or excuse me, the loss of A or the production of B? So there's something that we could do here. So again, do we take a look at how much A is losing down to B or how much B is coming up to A? Okay. So, I'm sorry, how much B is produced? Okay. Loss of A or production of B. And you'll see what we decide here in a second. Okay. So, and when we take a look at reaction rates, so here we have C4H9Cl reacting with water to produce C4H9OH and HCl. As you can tell, it looks like they are comparing, or we are comparing the C4H9Cl, the reaction of that. You start off with 0.1 at no time. So that's your original. And every time you move through here, this looks like this is wrong here. It looks like that should be, I don't know what that is. This is a typo. But as it keeps moving down, it keeps depleting. Okay, you keep reacting it, you keep using it up. Okay, so finally, after 10,000 seconds, you have none of it left, or something very close to none. Okay, so in this reaction, the concentration of butyl chloride was measured at various times. Now, moving forward, you'll notice that we have an average rate. So what we can do here is take the concentration divided by how much time passed. So you'll notice the change in concentration is delta. So, oh, by the way, brackets, such as you see here and here, means molarity. Get that in your head right now. That's molarity. Molarity, or in the form of concentration in the form of molarity. Okay, so notice we're taking a look at molarity. These are the brackets, so that's molarity, and it's molarities per second. Okay, so always know that those brackets mean molarity, moles per liter. Okay, so the average rate is taking the average over time. So we need to find the time interval each time we take each moment we take a time. Okay, so obviously we're going to find out the delta of these divided by the delta of these. Okay, so it's going to be this minus this divided by 50 seconds. Okay, so that's how we get that. Okay, real easy to find out rate as far as this goes. So let's keep moving here. So the average rate, as you can tell, if I'm going to find the average rate, is I'm just going to take the average of all these. Okay, so what happens to the rate as the reaction proceeds? Look at the question down here. What happens to this rate as it proceeds? The rate seems to slow. As a matter of fact, it does slow. So you start off with a rate that's very, very slow. And in other words, you consume a lot of reactant very quickly, and then it tails off to almost nothing. Okay, in a reaction like this, if we were to graph it. Okay, so what happens here is that our rate tends to slow because there's less reactant available to react. So just the fact that I have less particles that can do the reaction means the rate is going to slow over time. So when we graph this, you notice the plot of the concentration of butyl chloride versus time for this reaction would look like this, as I just drew. Okay, so it's concentration in molarity versus time. Okay, now what do you think the slope of the tangent line to the curve of this point represents? Okay, so what do you think the slope represents? It's obviously rate. Okay, so anytime I take this here or this here, this so we get into a little bit of calculus, although we won't be, don't worry, everything's going to be algebra based. Whenever we talk about the tangent of those curves, that's the rate at that particular time. So what do we call that? That's the instantaneous rate. Okay, the instantaneous rate. Unfortunately, we won't be dealing too much with instantaneous rates. We'll be looking more at the averages, okay? All reactions slow down over time, therefore the best indicator of the rate of the reaction is the instantaneous rate at the beginning. So whenever we measure the instantaneous rates or the instantaneous rate method, we're going to always do it right at the beginning, right here. What is it like at the moment it moves on? Okay, that's a standardized way of looking at this. Okay, so we will always take a look at the instantaneous rate at the beginning. Okay, now I just mentioned that we will be taking a look at the average. That's true. We will be looking at the average, but the instantaneous rate at the beginning is what we tend to measure. Okay, that's our standard way of looking at that. If we would measure 3 seconds into it, well, what if we did like one that happened over days? So you'd have almost no rate of change if you measured it 3 seconds every single time. Okay, so our standard is right when the reaction starts. So you'll notice that in this reaction, let's read this, the ratio of butyl chloride to butyl hydroxide is 1 to 1, okay, here to here, all right? Thus, the rate of disappearance of C4H9Cl is the same as the rate of appearance of C4H9OH. So in other words, since it's a one-to-one reaction, the stoichiometry tells us that the moment that these things disappear, the moment that this disappears, this appears, okay? So therefore, the change is the loss of this is equal to the appearance of this. So the disappearance of this is equal to the appearance of this, but not quite equal. Don't forget the negative sign. That's why is the minus sign in front of that? Because we're losing it. We're losing it. So that negative means something there. Okay, so the loss is obviously a negative type of thing, and therefore you see negative slopes, don't you? You see negative slopes here. So that makes sense. Okay, now what if we were to graph this stuff? We would see this, an opposite, where we have positive slopes at any instant. Okay, now initially the instantaneous rate is 0, isn't it? Because I don't have any of that right at the beginning. Okay, so this is of course a product. Let me just show you again. This is the product I'm considering right here. Okay, moving forward. Reaction rates and stoichiometry. What if it's not 1 to 1? Okay, so if we're not comparing something that's 1 to 1, we just have to simply consider the stoichiometry here. So in order, let's look at this. For every 1 mole of I2 that's produced, 2 moles of HI must be consumed or decomposed. So the rate of disappearance is twice as fast. Let me say it this way. The rate of disappearance of HI is twice as fast as the appearance of I2, in this case, or H2. Okay, so this will be consumed twice as fast. This stuff will be consumed, appear half as fast, if you want to consider it that way. Okay, so when we do this, you must consider the stoichiometry when we talk about this stuff. Now, we're not going to do this a whole lot in this way. So I'm going to move forward and see if we can't talk about a couple of these questions here. So again, try these on your own. It says, you can read the question. Let me show you the answer, and we'll go over these in class. Pause when you need to. So it's C. Okay, so I have a reaction from A to B, both gases. Don't forget brackets mean concentration, moles per liter. Peroxide disulfate ion. That's a different one. Here's, pause when you need to. Here's the answer. Okay, don't forget when we're talking about rate, we're always talking about time. You have to have some unit of time in there. Just showing you answers here. This is a little bit of a downtime, but I'm going to get to something else here. And pause it when you need to. Challenge yourself a little bit. Okay, we will go through all these in class if you have questions. Write them down if you think you need to. I don't know if I advanced the slide or not. I couldn't tell. Couldn't show you that one again. Okay, let's stop there, and we'll move on to a different video next. Email me with questions.